Hello and welcome to another geometry video. Today we're going to run through the notes from the textbook and bring up our proportions now in 3D. Proportions with volume for today. What happens when you have similar objects in 3 dimensions? Well, when you are dealing with 3 dimensions, I hold my stylus and pulled up 3 fingers at the same time? That is the question. When you're dealing with 3 dimensions, remember you need now 3 perpendicular measurements. Okay? So taking a quick look at example A here in the text, are these rectangular prisms similar? Notice that we have to compare all of their measurements. The height, 2 versus 2. The width, 3 versus 6. And the length, 7 versus 14, right? 7 over 14, that is equivalent to 3 over 6. So those 2 dimensions are proportional. But because that third dimension is not, then the objects overall, as 3-dimensional objects, are not proportional. They are not similar. Now you could look down, say, just at the rectangle, the top face, as it were, in this case. Right, because it was the height that broke the ratio. Just the rectangular faces, those parts are similar, but the overall rectangular prism, the 3D object, doesn't meet all 3 dimensions. It is not similar. Okay. What about dealing with cones? Here it's a little bit trickier when we add circles into the picture because this circle is itself a 2D object. It has dimensions in 2 different directions, even though they only give you 1. This radius drawn in here, this radius of 12, is also the same radius front to back there. Remember, the picture's a little distorted because we're looking at it at an angle there. So that radius actually does give you 2 dimensions, plus the height of the cone gives you all 3. So even though it looks like they've only set up a ratio between 2 sets of measurements, remember, radius is a cheat. It actually represents 2 dimensions already. So that's kind of convenient. All right, if you've been listening and paying attention, maybe you'll know where I'm already going with this next investigation. What about the ratio of the volumes itself? How does that compare to the ratio of the lengths, right? If I want length 1 to length 2, how does that compare to volume 1 to volume 2? What is the relationship between those ratios? Let's use their little block snake here for an example. If we had our little snake friend made out of these 4 blocks, we could say its length is 4. Oh, but what if we wanted a bigger snake, right? It's they suggest here, multiply each edge length by a scale factor of 2. Each length by 2. So our snake would actually become 8 long, but don't forget the other dimensions. So it was 1 wide, now it becomes 2 wide. It was 1 block tall, now it becomes 2 blocks tall. So instead of a 1 by 1 by 4 snake, we now have a 2 by 2 by 8 snake. Let that sink in. I doubled each of the measurements. And just to describe the rectangular prism built, I listed all the measurements. It's a 1 by 1 by 4, right? You see this a lot with lumber, right? Literally buying 2 by 4s to build houses, right? So this is a 1 by 1 by 4 snake. Double all the dimensions. Now it's a 2 by 2 by 8 snake. Notice each of those numbers got multiplied by 2. 'Cause that is what they told us to do. And that is what is required to make it similar. Each measurement must be multiplied by the same factor. The growth factor, or the ratio, scale factor, any of those terms, right? from any of these lengths, let me draw with another color here, right? From length 1 to length 2, I multiplied by 2, right? Started with 4, now it's 8 long. For width 1, width 2, height 1, height 2, all 3 dimensions. What does that do to the volume? Take a look at them. This is already set up to give you your answer. What is 1 times 1 times 4? 4. What is 2 times 2 times 8? Well, 2 times 2 is 4, and then 4 times 8 is 32. Oh my goodness. How much more is 4, or so how much more is 32 than 4, right? What do I have to multiply by to go from 4 to 32? Well, I just did that. That was 8. So even though I doubled each length, the volume is multiplied by 8. That is a drastic difference. Instead of times 2, it's now times 8. Where do you get 8? Why would multiplying by 2 3 times give me 8, right? Times 2 times 2 times 2. 2 times 2 is 4, times 2 is times 8. That is what I did. I multiplied by 2 3 times over, multiplying everything out. That is the same as taking the original and multiplying by 8. So, we can conclude that if corresponding, let me underline here, right? If corresponding edge lengths or radii or heights of two similar solids compare in the ratio m to n, so that could be 2 to 1, it could be 5 to 7, doesn't matter what it is. They set it up as the 2 letters just so we can see the effects on both parts of it. Then their volumes will compare in the ratio of, well, let me pause for a moment here. Remember what happened when this was area, right? Area gave us the m over n squared, because area is a 2-dimensional measure. So if volume is a 3-dimensional measure, what number do you think I'm going to put there now? Let me just move this out of the way. The volumes will compare in the ratio of m over n cubed. Take that ratio and cube it, right? And if you're not sure what 5/7 cubed is, remember that our power of a quotient exponent rule, we can represent that as m cubed over n cubed. So in this case, the 2 over 1, 2 times 2 times 2 becomes 8, or 8 over 1. 5/7 cubed, you can represent as 5 cubed over 7 cubed, which is, no, I really gotta move this out of my way. 5 times 5, 25 times 5 again, 125, and now I don't remember 7 cubed off the top of my head. 49 times 7. I apologize for taking extra time out of the video to do some multiplication. 4 times 7, 28 plus 6, 34, 343. I really should have that one locked down. 7 cubed is a wonderful little number to know because it comes up at times like this. 125 over 343, right? And that is what is the scale factor between the volumes, right? You should take volume 2, whatever one is bigger or smaller, right, will equal that ratio times volume 1, right? When you go to do these problems, oftentimes they'll give you one volume, they will give you the ratio of the side lengths, and they'll ask you for the other volume. So take that ratio, cube it, okay? If 5 over 7 was our r for ratio, then we want r cubed, or m over n cubed, however we want to think of it. Take that number cubed and multiply by 1 volume, or divide depending on which direction you're going. Watch out. Remember, a fraction bigger than 1 is going to make things bigger. A fraction smaller than 1 is going to make things smaller. So look, who wins? Numerator versus denominator, okay? Really bad time to start forgetting some of those fraction basics, but I know it. Things get hectic and it kind of gets lost in the shuffle there and forgotten. So don't forget those fraction elements. They come back again. All right. Other than going through a whole nother example with you, I really want to keep this video short. So that is all the content, right? And then you're on to exercises. There's one just like I was saying. Here's what they give you. Find the volume of the other one. Okay? It's not that bad. Take the number, cube it, and Bob's your uncle. Okay? If you have any other questions, please let me know. Comments below, Google Classroom, or find me on the Discord server. Or you can send me an email. That's 4 different methods you have of contacting me. Use them. All right? That's all the time I have for today. I hope you enjoyed the video. It was useful for you. So long. Farewell. Enjoy the rest of your day.